Hi, I hope you guys are doing well. This is our number 11th lab. It's about jumping mechanics. And before you watch this video, I hope you've already read the article I've posted in the beginning of the module, which is studying about a counter movement jump and comparing with arm swing and without arm swing, and what's the underlying mechanism causing higher jumping height for with arm swing. And if you haven't read the article, it would be better if you can go back to at least scan through the article so you'll know what we're doing for today's lab. So I assume you guys have already read the article, and here is the graph from the article. The upper row is about a counter movement jump with arm swing, and this is a counter movement jump without arm swing. And there are like two phases during a counter movement jump. One is a descending phase, the second is an ascending phase. And for today's lab, we're going to put a force plate beneath the feet so you can get ground reaction force during a counter movement jump. Okay, and if we have ground reaction force, what can we get from it? So you can take a look at these three common equations. The first one, if you have ground reaction force and you have the mass of the subject, you should be able to calculate acceleration, right? And then with acceleration, you can get velocity. And with velocity, you can get displacement. So these are three variables that we're trying to get from ground reaction force data in today's lab. Okay, so before we really calculated the variable, can take a look at how it should look like, at least get some sense before we really calculate it. So this graph and this line doesn't really match together, but it'll give us a little bit of sense. So we're looking at force here, which is this line. So you can see in the beginning, the net force is 0, right? Because there is no movement at the center of mass. And then at the descending phase, the force is negative because the center of mass is going down. And then at this point, the force comes back to 0, which means the ground reaction force is the same as the subject's body mass. And then the ground reaction force starts to incline. And then at this point is a point of takeoff. So there is no force on the force plate. You go to the lowest part here. And after the flight phase, the subject go back to the force plate. So you'll see a really high peak here. Okay, so for this force, we're talking about net force. And if we want to draw a free body diagram for this human, you can see there are two forces. The first one is the weight of the subject. The second is the ground reaction force that we'll get from the force plate data. And this graph is representing the net force. So initially the net force is 0, means ground reaction force is the same as your weight. But then when it goes down, that means the ground reaction force is less than your weight. So the gravity is pulling your center of mass down at this phase. And then your leg is generating force from the ground. So ground reaction force is actually larger than your weight at this phase. Okay, and the acceleration is will have the same trend as force. And then for velocity, this is a curve for velocity, this one. So you can see initially there is no velocity, but then at the descending phase, velocity is going down. And the entire part is going down. Then this part is 0 velocity, which is at the lowest point of your descending phase. And then you're ascending here. And then take off. So this is the highest velocity you can get from the ground. Then the this is the flight phase that you're in the air and gravity is pulling your velocity down. And at this point, when you have zero velocity, that means you're at the highest point. So if you combine these two lines, you'll see the highest point. This is the position. The highest point correlates with the zero velocity here. That means you're at the highest point where you don't have velocity, and then your velocity starts to become negative after the highest point. So positive and negative represents the direction in the graph. Okay, then how about displacement? You can see the displacement when you have negative velocity, your position starts to go down. And then at here, when your velocity is zero, that means you're at the lowest point of your center of mass. And then your position starts to ascend. And at the highest point, you also got zero velocity. So you can see zero velocity usually represents the highest or lowest point of our position. Okay, so that's like the 4 variables of counter movement jump. And we're trying to get this kind of graph from our force plate data. But how do we get the velocity and displacement from the ground reaction force data? We're going to use this kind of method. You can imagine this is an easy line. If the y-axis is acceleration and x-axis is time, then the area below the line will be velocity, right? Because velocity equals to acceleration times time. And if we change the y-axis to velocity and x-axis is time, then the area below the line will be displacement, right? Because displacement equals to velocity times time. So we're trying to find the area below the line, then you get velocity and displacement from force plate data. But we know our force isn't that beautiful. Usually it's irregular. So how do we find the area below the line with this irregular line? We need to use integration. So what does integration mean? Integration, like a simple example is that we divide the line into several segments. And each segment, if you link 2 points here, that represents a trapezoid, right? And we can easily calculate trapezoid area. So if we add all the trapezoid area together, that will be the area below this irregular line. So how do we calculate trapezoid area? It's not even high school math, right? It's like elementary school math. So for calculating the trapezoid area, you need an upper base and a lower base. Then you add it together. So this one adds this one, and then times the height divided by 2. So you get, in this case, that will be the height is 7 times the upper line plus the lower line, which is 12 plus 16, then divide by 2. You get ITA for this trapezoid area. And that's how we're going to calculate the trapezoid area in our force plate data. So imagine this line is when you connect all the force and make it on the x and y graph. So each data point represents time and the force. So y-axis is force and x-axis is time. So if we want to calculate the trapezoid area for this one, you'll need the y value for this line, for this point, and the y value for this point. When you add these two y values together and times the height, which is the time between 2 points, and then divide by 2, you'll get a trapezoid area. And I know it's a little bit hard to imagine, but I'll calculate it in Excel later. So when we practice more, you'll get more sense about what we're doing today. Okay, so that's all the background information for today. We're basically going to get ground reaction force data and use integration method to get velocity and displacement. And how do we integrate the force data? We calculate the trapezoid area below, like formed by each two uh, consecutive data point. Okay, I'll see you later in next clip.